Today's presentation is the first in a series of presentations I'm going to look at based on the papers I've presented at conferences such as the ATRF, ARB Conference, European Transport Conference, and Engineering and Technology Forum. The paper I'm presenting today, titled How Assumptions Influence the Results of a Cost-Benefit Analysis. This paper was presented at the 2016 ARB/ATRF conference. This presentation will be focused on the following assumptions. Base case, which is basically the scenario without the project, the as-is situation and going forward. Use of different models, so we could be talking about economic models or we could be talking about transport models. Incomplete information, so there'll be times when you don't have everything, well, almost every single time information isn't going to be complete, so therefore we're going to have to make some assumptions in order to cover that incomplete information. There's various ways of going about that, and it's often not completely consistent with other projects. User behavior, which is another interesting one as well. Again, that's something that has to be projected forward and something that has to be predicted given changing circumstances. Forecast demand, again, that can be linked to user behavior as well, but it's projecting demand going forward and the extent of growth, even if there isn't any change in behavior. So it could be the same behavior, but just at a growth rate. Is that following population growth? Is that following growth in GDP? Depending on the scenarios. The base case is probably the most important assumption to get right in a cost-benefit analysis. It is your yardstick for what you're comparing all your benefits against. It is your current situation, your as-is, and it is also what will happen going forward in the event that the project does not go ahead. And the key to this is that the base case needs to be as realistic as possible. So we can't have a situation, as you can see here, where the world is falling apart simply because we did not build a project. It's got to be as realistic as possible. So in a sense, it's got to look at future behavior going forward. How will people adapt if something is not done? Also, potential investments that are made. Even though these investments are not going to be of the magnitude of the project, but they're going to have to be, to a certain extent, able to cater for whatever problems the base case is actually presenting. So in a sense, you shouldn't have a do-nothing scenario in your base case. Your base case has to include all of these behavioral change and future investments. This is generally not popular amongst analysts because it tends to make the project worse. In a sense, you've got a realistic base case where you can actually compare your options against. May not look as good if you look at a scenario where the world is falling apart and the project is a must-have simply because it is that bad. And another problem with having a base case that is that horrendous is the fact that almost any project you put forward is going to look good by comparison. And it may mean a proper options analysis is not being conducted. The first project I'd like to take a look at is the Arnot Creek Bridge upgrade. Arnot Creek is located along the Bruce Highway just north of Townsville. And this project is a bridge upgrade basically because the existing bridge is not up to standards. It can't take the weight loads of some of these big trucks that are traveling up and down the Bruce Highway. Therefore, it needs to be strengthened. Otherwise, the bridge is going to either have to be closed, load restrictions, or limited to one lane in order for it to not collapse, which would be a real problem. So assuming that that scenario is not going to take place. So again, we have a scenario where probably it's going to be closed and vehicles are going to have to take an alternative route. The problem with this was not so much the assumptions around the closure, but there's an assumption around an alternative project that was actually being developed, which was called the Cardwell deviation. And there's a bit of an unknown factor when this was actually going to be built. If it was going to be built maybe 5 years out from now, upgrading this bridge would have very little value because the heavy vehicles would be diverting onto the new road, which is the deviation, which is a much better quality road than the existing Bruce Highway. But if this upgrade did not take place for another 15 years, then this bridge is going to be fairly critical. In a sense, you'd have about 10 years of heavy vehicles taking a very long diversion route in order to continue going backwards and forwards north and south, which would actually probably pump the benefit cost ratio up to around 100, compared to if this upgrade wasn't really needed, if the cardboard deviation was actually completed in the next few years. So again, it's critical to know when alternative projects are going to be built and how that affects your base case. In a sense, a base case where the cardboard deviation goes ahead is a lot stronger and is going to make this project a lot worse. If that project does not go ahead, then the Arnot Creek upgrade is going to be necessary, in the sense you can have a very bad base case where vehicles are diverting along alternative routes. A key input into any analysis is the use of models, whether it be the transport model that provides the input into the economic model, or the economic model itself. And what's important here is you get the right model to fit the right project. If it is an enormous project, you might want to use a macro model for your transport modeling, and then you'd have an economic model that can cater for the macro outputs. If you've got a much smaller project, then possibly you would use a mesoscopic model or micro model, and again you'd need the appropriate economic model for those inputs to go into. And the results out of those models could be very different. There's a macro model, you're incorporating a lot more things into it, a much larger part of the network, but it's far less focused on the upgrade. And that is good for projects that are very large and affect a very wide area. If you've got a project that's only going to affect a very small part of the network, then a microscopic model is probably going to be far more appropriate. And again, you need to have the right economic models to go with that, and the models that can actually handle those inputs. So we're going to have an example up next that actually looks at two different models. In this case, they were both mesoscopic models, and how the results of some transit lanes actually varied quite a bit based on those two different models used. So for our example, we've got the Brisbane Northern and Eastern Transitways. The Brisbane Northern Transitway used the mesoscopic model, the Visum mesoscopic model, whereas the Eastern Transitway used the AIMSUM model. Those models are a little bit different. Visum covers a much broader area than what AIMSUM does. AIMSUM will be a little bit more focused on within the area, and it was also looking at intersections a lot more closely, whereas Visum was actually looking at a broader area, so therefore was incorporating it a lot more. As you can see from the slide, the Eastern Transitway, using the more focused model, produced a much lower benefit cost ratio, whereas the Northern Transitway, which included a lot more of the network, produced a much higher benefit cost ratio. The two projects are very similar in nature, as they were both within Brisbane, offering very similar upgrades, but you'd expect them to have quite similar results. So it's quite likely that the two different models actually influence the results. And you can actually look at a previous analysis that was done. This did not state the models that were used, but the Eastern Transitway got a benefit cost ratio of 1.6, whereas the Northern Transitway got a BCR of 1.8. So they're far more similar back then to what they are in the most recent analysis, where we use different models. Again, I'm not entirely sure if the models are entirely to blame for the results, but it seems to be a good indication that the model that's included more has produced the higher benefit stream. The Coomera Interchange is an example of where different models were initially used. The Sidra model was used initially. It found it was problematic because it wasn't picking up the effects of multiple intersections within close proximity. Therefore, changed it to using the AIMSUM model, which is actually better adapted at looking at interchanges and intersections that were within close proximity to each other. But the results pulled out the AIMSUM model only accounted for the peak periods, so about 1 or 2 peak periods per day, roughly 1 or 2 hours of peak periods per day, and that did not account for the off-peak benefits. Analysis wasn't conducted on that, and I think it was believed that there wasn't significant changes during the off-peak periods regardless, because there wasn't a congestion issue at the interchange. But the analysis was conducted, though, assumed that 80%, I think it was, of the benefits were actually the off-peak benefits based on the distribution of time, and also based on some information, I think that was out of the BTRE, that indicated, what did it indicate? I think it was about 80% of the benefits actually came during, well, actually 80% of the cost, actually, and this was then translated, you get 80% of the benefits. Again, there isn't any supporting evidence, but the results were vastly different. You had a benefit cost ratio that was considerably higher. It was around 2 when we included the off-peak benefits, but without the off-peak benefits, it was well below 1. In fact, it was, what do we have here? It says it was, here we are, about 0.1. So it's quite dramatically different considering the duration of the off-peak period compared to the peak period. Again, it's difficult to support either. Personally, I would go with a more conservative approach and actually go with the lower benefits based on the fact that there's not supporting modelling for the off-peak period. Incomplete information is another interesting problem that needs to be worked around, and assumptions often need to be put in place in order to fill the gaps left by incomplete information. So if the time permits, again, further research can go into acquiring information to fill those gaps, but that's often not possible. So there needs to be alternative approaches in order to do that. And again, consistency between projects would be great. Like, for example, you could use rules of thumb. Let's say over like maintenance costs, for example, you may have a certain rate that has been established for roads of a certain nature that can be applied to this project. But it's often difficult because project teams don't necessarily work particularly closely to each other, or within programs are often working in isolation. Therefore, they're not necessarily aware of assumptions that have been made in other projects, and incomplete information can be treated quite differently, and it can actually change the results of analysis quite dramatically depending on what those assumptions are and how those gaps have been filled. An interesting example of incomplete information is the Maroochydore Road Interchange. So that's the interchange of Maroochydore and the Bruce Highway, which is somewhere up at the Sunshine Coast. Maroochydore Road Interchange was actually looked at in the paper for 3 different scenarios. The first one was actually the base case in terms of base case definition, and that's covered off in the paper. I won't cover that off here. And also it was looked at in terms of modelling as well. But in regards to incomplete information, we're looking at the years modelled. Only 2 years of modelled for this project, and the final year was actually modelled in 2031. So the remaining years, which is about another 20 years of benefits, weren't actually modelled. So in a sense, that had to be completed through an assumption about regarding the benefits for that extended period. So what actually happened was the economists that actually looked at this assumed that benefits were declining for a period of about an extra 10 years and eventually non-existent for remaining 10 years, which is sort of a balance between, I guess, having high benefits of assuming that benefits are going to remain constant for the remaining 20 years, or the other option would be to cut the benefits straight off at year 2031, and providing a residual value. This approach potentially could underestimate the benefits. So there's a range of results. We'll look at that in the result sheets later on for applying this. But considering there's 20 years of benefits, that could potentially affect the results quite significantly. User behavior is one of the most difficult assumptions to predict. It's very hard to know what someone's going to do, especially if there's no prior information about what they've been doing. An example of that would be if you were to put a new train line in to an area that's never had exposure to train lines or even public transport for that matter. How many people are going to get out of their cars and use the train? How many are going to switch from buses to train? How many people are willing to walk to a train station or possibly cycle to a train station? It's difficult to know. We may have information about what people have done in other areas and for other projects, but can that necessarily be applied to your project? Again, people in different areas have different perceptions, and it can be very difficult. Another example would be, how do people respond to flooding? Do they not travel? Do they engage in alternate activity? Do they wait for the floods to clear? Or do they take an alternative route? So the project that we're looking at here in regards to user behavior is actually a flood project. Haughton River floodplain is located between Bowen and Townsville along the Bruce Highway. And this area is prone to floods. I think almost every 2 years there's a flood event that occurs there. Closures are generally not that long. We're talking about maybe a couple of days on average per year. But potentially the cost of that could be quite great because the Bruce Highway is the main route travelling from north to south or south to north, from Brisbane all the way up to Cairns. And there's not too many alternative routes that vehicles can use, and that's especially for heavy vehicles that tend to be taking the entire route, compared to maybe some local traffic that I suppose can, forego travelling for 1 or 2 days if they're working within the area, or maybe engage in alternate activities. But what makes it difficult is to predict what that user behavior is going to be and how's that going to influence the results. Now, you can see there's 2 ways of going about it. We can take assumptions that are being made by people on the ground, people that work within the area, or you can take a cost approach in terms of what is the lowest cost alternative in terms of how many will divert and how many will wait. For example, if you have a very long flood and the road is closed for many, many days, then there's going to be a much higher tendency to take an alternative route rather than to wait. If the flooding is going to not last for too long and closures are going to be for just maybe a few hours or a day, then waiting might actually be a better option. So the approach that we took for the Haughton River floodplain was to assume the lowest cost approach. So for example, if waiting was the lowest cost approach, then we'd assume that the vehicles would wait. This again changed depending on how close you're actually getting to the time of closure. So at the very beginning of the closure, you might have vehicles that are willing to divert, given that, let's say, the diversion takes another few more hours compared to actually waiting maybe 10 hours. You've got to bear in mind the cost of fuel and all of that. Once the cost of time for waiting is actually less than the cost of actually diverting, bear in mind that waiting time actually has a value, and we've got some values to calculate that. Then you assume that users are more likely to actually wait for the road to reopen again. Again, we got some different results depending on how we assumed, or what we assumed. So using the cost approach, the benefit cost ratio, I think it was at 7%, was very low. It was only 0.15. If we made an assumption that vehicles were actually going to divert, then a greater urgency that you can't actually wait, then the benefit cost ratio would then climb up to 0.33. In this case, both scenarios have produced actually very low results, indicating that upgrading the Haughton River floodplain probably isn't a particularly good investment. Simply not so much because of the benefit side of it. There's definite benefits and cost savings by reducing the flood times, but to actually upgrade the Haughton floodplain costs around, I think it's about $500 million. So your benefits again may only be about $100 or so million. In a sense, those benefits do not cover your costs, so therefore it would not be a worthwhile investment. And both scenarios are indicating that. Though one scenario is indicating where benefits almost double compared to the other. So again, user behavior can have an impact, and if the numbers were a bit higher and closer to 1, the assumption of all diverting would probably get the benefit cost ratio above 1. Forecast demand is a very interesting assumption. Again, most of the projects I've worked on were basing future demand on past demand. And for what I've seen, it generally follows a pattern, and normally demand follows for roads anyway, a linear growth pattern. And normally, even if it is out by a couple of percent, if you got your current demand correct, then normally just up or down a little bit on the percentage doesn't make too much of a difference. The real difference comes when you're looking at a new road or you're looking at a new area that's developed, and there's not an awful lot to base it on. Then basically your current demand doesn't exist. So basically everything is based on your forecasted demand. And we're going to look at a project now that actually didn't have any traffic at all because it was an industrial area that was being developed. This project is the Gracemere Overpass. Prior to the project, and we're looking at with Gracemere, we're going back a few years now, I think it was around 2011, 2012. There was a proposed industrial area just west of the actual residential area, and access to that area was rather limited. And that was based on the fact that vehicles had to cross the railway tracks. And those rail crossings tend to be quite unsafe. They didn't have the boom gates, they just had the flashing lights. Trains were fairly frequent, so if you've got plenty of traffic going across there, you could have quite substantial delays. So in order to fix that problem, an overpass was proposed, and the rail crossings were closed. So with the overpass, vehicles could then just cross the overpass without any form of delays. This project, again, I think we're looking at about $50 million, which would not be worthwhile considering there were very few vehicles actually accessing that area at the time. But the benefit cost ratio for this project ended up above 1, and that's simply because of the high forecasted demand. We're expecting this industrial area to grow quite significantly. It's going to exceed 4,000 vehicles within the first 20 years and is eventually to exceed 11,000 vehicles. So with that high demand, that actually pushed the benefits up quite substantially. But the problem is, this is just forecast demand, and also we don't know whether that industrial estate is going to grow as predicted or if it's going to grow at all. And currently that area is actually fairly undeveloped at this stage. Still, I think we've got to wait a few more years in order to determine whether any of this demand is going to, like you say, it could just suddenly start growing. As part of the sensitivity analysis, I assumed half the growth, and that actually dropped the benefit cost ratio down to 0.5, and indicating then this project is not economically viable based on half of that demand, which may turn out to be the case. I would like to now summarize the results of the projects we've actually investigated so far. So the first one we started off was the Arnot Creek Bridge, and what we looked at there were base case interventions. So we have a low benefit cost ratio of 0.75, and that was based on the assumption that the Cartwell deviation was going to be built reasonably soon, and traffic wouldn't be required to divert. So basically we're looking at mostly safety benefits for vehicles that would not be using the upgraded Cartwell deviation. The high BCR, on the other hand, that is assuming that the Cartwell deviation is not built for maybe another 10 to 15 years. And if Arnot Creek is not upgraded, they're going to have to divert and use alternative routes or not travel. And that for even 5 to 10 year period is going to be very, very costly. You're going to have a very high cost in the base case, therefore producing very high benefits for when it is actually upgraded. The next project we looked at was the Coomera Interchange. This investigated transport modelling. So we got a low benefit cost ratio when we looked at the AIMSOM results for just the peak period, which is limited for about 1 or 2 hours in the AM and the PM. And the high BCR is if we assume there were off-peak benefits, and these off-peak benefits were again in line with the assumption of costs occurring throughout the day. So again, that would only work if the costs were actually lower, significantly lower in the project case. There wasn't actually any evidence provided indicating that there are actually going to be off-peak benefits. Though it's possible there could be, but on a cautious side, it's probably more likely going to be closer to the low BCR that was provided. Corroy to Curragh Section B, I did not cover off in this project, but this again looks at demand forecasts. Just very quickly cover that one now. So there was a difference of about 1 or 2% in the growth forecast, and that actually raised the BCR quite substantially. Again, wouldn't normally see such an increase based on maybe just a small increase in percentage growth. But what happened was congestion set in a few years earlier, and therefore because of the discounting effect not being so great, those congestion costs greatly raised the benefits if we assume that congestion is going to be earlier because of the higher growth rate. The Gracemere Overpass, again, that looks at demand forecasts, which basically we didn't have any evidence going forward about what that growth is going to be. So it was modelled based on the expected growth in the industrial area. High BCR, assuming it goes according to plan, gets you just above 1. If we assume half of that, gets you just a 0.5. Haughton Floodplein, both of these benefit cost ratios are rather low. One of them 0.15 based on users adopting the lowest cost approach. And the high benefit cost ratio is based on vehicles diverting to avoid the closure, which is also possible as well if the timings of the closure is unknown or some uncertainty about when the road's going to open. A high percentage of vehicles may just choose a diversion route. Again, though, even with a diversion route, there's the potential you could have other closures as well, because there tends to be flooding within the network. So again, those diversion routes could be longer than it was anticipated. So you could actually get a benefit cost ratio that exceeds 0.33. The Maroochydore Interchange, that was an interesting one in a sense. I didn't cover off on all of that. So with the base case, there was an assumption around what is the most realistic base case. One was a do nothing scenario, which it was compared with, and we got a BCR 4.8. And then there was a do minimum scenario, which was to actually put signals at the interchange. The economic modelling, how that differed, I think we covered off on that one. Again, that was looking at in terms of the years of modelling. Do we extrapolate benefits out for the remaining 20 years, or do we cut the benefits short? So that created quite a difference in results, going from 2.1 to 4. With the transport models, we looked at Transitways, eastern and northern. So again, the difference is in terms of the assumptions applied and also the models that were used. So you have a model that's more inclusive of the greater network like VISM, it will produce a higher benefit cost ratio compared to AIMSUM that was more focused on the actual upgraded sites in themselves, which produced your much lower 1.43. Bear in mind, they're actually two different projects. So those results could vary a little bit because we didn't have the results for one project in particular. So how do we solve this problem of assumptions and the effect that they have on results? One possible approach is to look at sensitivity testing. So you look at a number of different sensitivities. So for example, you can look at high, medium, low growth rates. For example, you can get a range of results. Again, you can look at mode shift. Does 10% of people switch to trains, or does 30 or 40%? And you'll get different results that way. Again, there's still an issue of consistency between projects. And you could, on top of that, you could also apply Monte Carlo analysis. So that would there, like you can see in the graph, that would generate your results from P90 all the way up to a P10. I think we have in the graph, we have P50s, P70s. So basically what a P is the probability that your results are going to be greater than that. So we've got here the benefit cost ratio. So you would see that the P90, there's a 90% chance it's going to be higher than what's shown in the graph. There's also P70, again that's a 70% chance it would be higher, and a P50 which is a 50% chance. So you've got Project B, which has got a much broader distribution compared to Project A. So therefore the results could be higher for B or it could be lower. Again though, which results would you compare if you're trying to prioritize? Would you look at the P90s, which then Project A would actually look more favorable, or would you look at maybe the P50s, which Project B would probably look more favorable? But B, obviously by the wider distribution, tends to be riskier. So if you're being risk averse, you might look at the P90s. But generally, in terms of results, we look at the P50s, which would then favor Project B. Again, there's also the problem of assigning probabilities to various sensitivity tests that have been applied. And if that's not done consistently between projects, it's very difficult to make a comparison, even with the use of Monte Carlo analysis. What has been proposed in this paper to address the issues of assumptions is a program approach, which means you're actually looking at it as from a whole program perspective. So you'd have a program of multiple projects with certain independencies, certain relationships between them, and then developing a set of assumptions that you can actually apply across the projects for consistency. So for example, if you got projects within the same area, you would use the same growth rates potentially. And again, if you're looking at mode shift as well, you'd have the same percentage mode shifts linking all of your projects together, so one's not going to stand out over the other. And that would help you actually improve your analysis. Again, by using a program approach, you would actually have more transparency as well. In a sense, you would be bringing assumptions across various projects, and you'd be able to see the relationship and how they connect with each other. And by having a broad set of assumptions as well for an entire program, it actually saves time. You don't have to develop them individually for each project. And by actually having a program, by having that level of transparency and also that level of consistency, it'll help decision makers decide which projects should be prioritized within the program. So if you're looking at a program as something where you would try and have a fixed amount of funding, and then you're trying to utilize that funding with the optimal selection of projects. Back on the topic of consistency, which I think is probably what I see anyway, the greatest benefits of using a program approach is the fact that it can potentially solve the problems that we've identified for all of the projects. So again, if you have consistency with the modeling, so you may want to allocate just one particular model for that entire area. So you, for example, you could use Visum for that whole area, you could use AIMSUM and all that, and you'd be using the same models, the same calibration of models, and you have that same consistency. Of course, there's going to be some variances between the projects that may need some adjustment, but at least if you're working off the same model, you're not going to have complete inconsistency of two project teams not knowing what the other one's doing. Assumptions around incomplete information as well could be consistent. You can use the same rules of thumb across various projects. And you also identify, like for example, we looked at Maroochydore project earlier on, and the growth there went out for like another 20 years potentially. So you could again do that for all your projects. You could bring them all out by an extra 10, 15 years, or you can actually cut all of them. So in a sense, you are comparing consistently across the board. Whereas if you're going to compare a project that's got a life of 30 years compared to a life of 15 years, it's not a very reasonable, fair comparison. You expect the one with a longer project life, again, to produce more benefits. User behavior is another one as well, which you can have much greater consistency. Again, if you're looking at, like for example, a flood project, you may have several projects along your road. It may flood in like 8 or 9 different places. So you'd want the same consistent approach to user behavior. So if they're diverting for one, they may very well be diverting for all of them. Or if you've got the same sensitivity to weighting for one, that will apply across all of them. And again, it also helps you understand which ones are the key priorities. So you may have an area that floods for a particularly long period of time. And for those projects are probably going to be the ones you're going to need to do first. So let's say you have one part of the road that floods for 10 days a year and one only floods for 2 days a year. You fix the one for 2 days, you still have the 10 days of closure regardless. So you're basically not going to get any benefits by doing the 2 days. Whereas if you did the 10 days first, then effectively you're reducing 10 down to 2. And then you do the 2 day, the section that's flooded for 2 days, then you're going to get those additional benefits that you might not necessarily see if you've done the one before. So again, it helps prioritize by actually having it within a program. So this brings us to the end of our presentation. So I'm going to wrap this up with a simple conclusion. So basically, assumptions can have quite an impact on the results of any cost-benefit analysis. And we focused around a few different areas around base case being a very difficult one to predict, but then very, very critical, as we saw with Arnot Creek Bridge upgrade. Another one is the type of models that we used. So again, how far are we covering and how narrow are we in terms of our assumptions, in terms of what those models and economic models actually cover. Another interesting one is how you cover incomplete information. So again, what assumptions can we make to cover off on that? And again, can we keep that consistent with other projects, which is also a difficult one. So we came up with 2 possible solutions. The first one, I think that's been covered in a few other papers, and that's sensitivity analysis and Monte Carlo analysis. Again, it presents consistency issues, and also in terms of determining a probability can sometimes be very difficult with the information that we have. So what's been proposed in this paper is to look at it as a program, as in a collection of projects together and forming one program. So again, has to be a logical program. They need to be interrelated to each other in one way or another. In a sense, they are supporting each other. And the cost-benefit analysis can basically distinguish between those projects using very similar assumptions. So, for example, you'd be looking at similar growth rates, for example, or you'd have a similar approach to actually looking at incomplete information and potentially certain rules of thumb. Again, it's consistency being the big thing as the advantage of having a program. So again, I'd like to thank you for listening through this presentation. I think it's been fairly long. If you made it this far, thank you very much.
If you like today's video presentation, just click the like button and the subscribe button, and I'll be uploading several more videos in the weeks to come. Again, within the same series, videos relating to the transport conferences, as well as several other videos also relating to economics. If you want to find out more about today's paper, just go to my website at spectrumecons.com and you go to the research paper, just click the link there and you'll get the paper in full. Again, thank you for listening. Goodbye.